Let's look at a one-sided hypothesis test for proportion. Part 2. This is just another example. It is hypothesized that some people sick with cancer can temporarily postpone their death until after a major holiday. One study counted the number of cancer deaths during the week before Thanksgiving and the number of cancer deaths during the week after Thanksgiving. Formulate null and alternative hypotheses. The null hypothesis, as always, is no change, no difference. So it doesn't matter whether it's week before, week after, it should be the same. And the null hypothesis always has an equal sign. So it's of the form P equals some P0. The people in this study either died of cancer the week before Thanksgiving or they died of cancer the week after Thanksgiving. So nobody else, just people who died the week before or the week after. Let P equal the proportion of people in this study who died of cancer the week before Thanksgiving. The null hypothesis is that P equals a half. Because in this study, just people who died the week before, week after, shouldn't be any difference between the two, so we're just going to say the probability of dying of cancer before Thanksgiving should be the same as dying of cancer after Thanksgiving. So we'd say P equals a half. The alternative hypothesis is that there is a change, there is a difference. We represent that with H sub A or H sub 1. The alternative hypothesis always has a less than sign, or a greater than sign, or a not equal to sign. So it's of the form P does not equal P sub 0, or P is greater than P sub 0, or P is less than P sub 0. Okay, so here's one possibility. H sub A, P does not equal half. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the proportion of people in the study who died of cancer the week before Thanksgiving is not a half. Or if we wanted to test the hypothesis that the proportion of people in the study who died of cancer the week before Thanksgiving is a half. No, we didn't want either of those. P is greater than a half. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the proportion of people in the study who died of cancer the week before Thanksgiving is greater than a half. But that's not what we hypothesized either. P is less than a half. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the proportion of people in this study who died of cancer the week before Thanksgiving is less than a half. And that's what we hypothesized, so that's what we want. P is less than a half. We choose this as the alternative hypothesis because we want to test the hypothesis that the proportion of people in this study who died of cancer the week before Thanksgiving is less than a half. Let P equal the proportion of people in this study who died of cancer the week before Thanksgiving. The null is P equals a half. The alternative is that P is less than a half. There were 6,062 cancer deaths during the week before Thanksgiving and 5,938 cancer deaths during the week after Thanksgiving. Test the hypothesis that the proportion of people in the study who died of cancer the week before Thanksgiving is less than half. Okay, there's our null and alternative hypotheses. Let's calculate the test statistic Z. Well, we know what P hat is. P hat is the proportion of successes, and it turns out that there were 6,062 plus 5,938. In other words, 12,000 people in the study. That would be our N. P is the proportion of successes in the trials. P hat, I should say. That would be 6,062 deaths over 12,000 total people. Not sure death is really a success, but that's the way it works out in this problem. P0 is our conjectured value of P in the null hypothesis, and that is a half. Okay, so here's our test statistic. P hat, 6,062 over 12,000. P0 is a half. Plug that into for the bottom too. 1 half, 1 minus a half, N is 12,000. Z turns out to be 1.1319. Well, what does that mean? Z equals 1.1319 is our z-score. Assuming the null hypothesis is true, this is what the distribution of z-scores would look like. It's normal with mean 0, standard deviation 1. Again, if the alternative hypothesis, P does not equal P sub 0, that's two-sided, the rejection region would be Z is less than negative 1.96 or Z is greater than 1.96. So we would reject in either of those cases, if Z is too small or if Z is too big. If the alternative hypothesis is that P is less than P sub 0, that's what we have in this problem, then the rejection region would be Z is less than negative 1.645, because that's the bottom 5%. If the alternative hypothesis is P is greater than P sub 0, not what we have in this problem, the rejection region is Z is greater than 1.645. Again, it would look like this. Z is too big. So whether it's this rejection region or this rejection region or these two put together, it's all 5%. It's either the bottom 5%, the top 5%, or the bottom 2.5% and the top 2.5%. How do you know which to use? It all depends on what your alternative hypothesis looks like. Okay, our alternative hypothesis is one-sided, and it's of the form p is less than p sub 0. So we reject the null hypothesis if the z-score is too far to the left. Why only to the left? There's no need to embrace the alternative hypothesis p is less than p sub 0 if our data indicate a value of p which is much greater than p sub 0. So if you had a p that was over here, or even over here, you wouldn't embrace that alternative hypothesis. You would embrace the alternative hypothesis only if you had a value of p, only if you had a z-score out here, and that would correspond to a value of p that was pretty small. Since the default level of confidence is 95%, we reject the null hypothesis when the z-score is in the bottom 5%. This means we reject the null hypothesis when the z-score z is less than negative 1.645, which is about over here. So that's about 5% of the area. Okay, since our z-score is 1.1319, hey, that is not less than negative 1.645. In fact, it's positive. We do not reject the null hypothesis. We fail to reject the null hypothesis. Again, we don't say we accept the null hypothesis because we're never sure it's true, but we just say we fail to reject it. Kind of awkward. Find the p-value. What's the p-value? It's short for the probability value. It's the probability that we would get a result this extreme or even more extreme if the null hypothesis were true. If the null hypothesis were true, the probability that we would get a z-score of 1.1319 or even more extreme is, well, again, if the alternative hypothesis is p is less than p sub 0, that's what we have here. We want the area to the left of z. And so that's the area to the left of our z value. Okay, so in this case, ours is h sub a. That's p is less than a half. So we want the area to the left of z equals 1.131. Wow. Okay, so in this case, the area to the left of 1.131, that's the area to the left of this thing over here. So we would enter normal CDF negative 10, comma 1.131. Again, negative 10, there's no negative infinity button on the calculator, so negative 10 may as well be negative infinity. We get 0.87097. That is our p-value. So the p-value is 0.87097. The p-value is less than 0.05. If the p-value is less than 0.05, we reject the null hypothesis because there's a less than 5% chance we would obtain a result this extreme or even more extreme if the null hypothesis were true. If the p is low, the null must go. And that's what we do in this case. We had a p-value, well, that's not what we do in this case, actually. Our p-value is 0.87, so we do not reject the null hypothesis. We fail to reject it. P is the proportion of people in the study who died of cancer the week before Thanksgiving. There are our null and alternative hypotheses. We fail to reject the null hypothesis. There is not sufficient evidence to conclude that some people sick with cancer can temporarily postpone their death until after Thanksgiving. By the way, what day of the year sees more deaths from natural causes than any other? It's New Year's Day. A few years ago, a sociology professor named David Phillips examined 57 million death certificates issued between 1979 and 2004 and made an interesting finding. Not only do more people die in the winter months, but New Year's Day is actually the deadliest day of all. He plotted the millions of deaths from natural causes according to the day of the year in which they occurred. You get a sort of wave of death that ebbs in late summer months, rises sharply in December, has a peak at January 1st before subsiding more gradually through the beginning of the year.